In this section 3.5, we get a little bit of a break from derivatives. The focus of chapter 3 is really what does the derivative tell us about functions, both first derivative and second derivative. But in this section, we kind of step away from that for a little bit and we look at another characteristic of graphs, which is called end behavior. And end behavior can be found not with derivatives, but looking at limits. So our focus all day today is looking at what happens as I look at both ends of my graph. So if I look at a limit as x goes to infinity or x goes to negative infinity, those are called limits at infinity. The positive infinity is going to be my right end behavior. As I put bigger and bigger values of x in, I'm going to see what's happening at the far right side of the graph. And then as we look at my limit as we go towards negative infinity, this is going to be my left end behavior. Chapter 3 is really focused on functions and what we know about them. And so even though this isn't a derivative piece, it's still going to be something that we can tell about functions without having to grab a calculator or have some sort of aid in our graphing. So the goal today is if I give you a function, and we're going to work at a lot of rational functions today, meaning have a numerator and denominator, then you should be able to tell me what the end behavior is without having to pick up your calculator. So this function right here, 3x squared over x squared plus 1, I drew a picture right here. This is a screenshot from a graphing calculator. That is what that graph looks like. And what you'll notice is the end behavior is flattening. Both sides have what's looking like a flat piece going towards a horizontal asymptote. So this dotted line is a horizontal asymptote. And what it does is it kind of guides my end behavior. It almost serves like a guide rail to tell me like where's my function going. And my goal for you guys is that you can look at this equation and know what the end behavior is without having to graph it. And here's how we do that. The key is we look at the degree of the numerator and denominator. Degree is the highest exponent. That's a word from Algebra 1. If the degree is the same, which is what you're looking at in this one, you have an x squared on top and you have an x squared on bottom, your limit, or looking at your end behavior, will be the ratio of your leading coefficients, which are your first numbers. So you have a 3 over x squared and 3x squared over 1x squared, which is a ratio of 3 over 1, which tells me that my limit as I go to infinity or negative infinity is y equals 3. That creates that end behavior that is flattening on both ends, and it creates a horizontal asymptote to show that flattening. So my goal today is to go over a few guidelines specifically focused on rational functions and how we know what's happening at the ends without having to graph it ourselves. So we have 3 guidelines. I always call them limit guidelines or guidelines for limits to infinity. And they really focus on what are our options with our degree of our numerator and denominator. So option 1 or guideline 1 is what we just talked about. It's when the numerator and the denominator have the exact same degree. So for example, an x squared over an x squared or an x cubed over an x squared over x cubed. This limit, and it does not matter if this limit's going to positive or negative infinity, will look something like this. So let's say it's 4x cubed plus 7 over 8x cubed minus 2. As soon as you realize that both the top and the bottom are x cubes, then my limit will be whatever the ratio of their coefficients are. So in this case, 4 over 8 reduces to 1/2 if you'd like, or you could write as 0.5. That is my limit as I go to infinity or negative infinity. This would be true if it was positive or negative infinity. What that means is that I have a horizontal asymptote. I always write HA for horizontal asymptote at y equals 1/2 because that's what's going to guide my end behavior to the left and to the right. Anytime we get a finite answer for this, we will get that horizontal asymptote at y equals that value. Essentially what's happening here is you're saying, well, the top and bottom are essentially growing at a very similar rate. They're both growing growing as a cubic function. So if we take the ratio of those coefficients, we can figure out what will happen as we get bigger and bigger or smaller and smaller numbers in for x. So that's the most common guideline. It's also the one that students tend to be the most comfortable with. My second option is what if the bottom has a bigger degree than the top? So for example, and this is also true for positive or negative infinity, let's say it was 4x squared plus 7 over an 8x cubed minus 2. So the bottom is a third degree, the top is only a second degree. If the bottom has a bigger degree, essentially it's growing faster than the numerator, which eventually is going to make my number get smaller and smaller and smaller. If you think about dividing by something that's bigger and bigger and bigger, the effect is shrinking the actual answer. So what my limit will be 0 for this, which means that my horizontal asymptote is going to occur at y equals 0. It's going to happen right around the x-axis, and you're going to have that flattening effect on both the right side and the left side towards 0, towards y equals 0. And then my third option is, what if it's flipped? What if the top has a larger degree than the bottom? So for example, I'm just going to take the one we just did and flip it upside down. What if it was 8x cubed minus 2 over 4x squared plus 7? With this, because the numerator is growing faster than the denominator, it will continue to grow bigger and bigger and bigger. The denominator essentially can't keep up because it's not growing as fast, since it's only a second power as compared to the third. And you're going to get a limit that will eventually get bigger and bigger to infinity. Delta Math will say, well, this limit doesn't exist because it's not a finite number. So you can just put DNE in that case. This one will have no horizontal asymptote because it doesn't flatten. It just keeps getting higher and higher. My end behavior will actually be infinite end behaviors. They're either going to go up indefinitely or down indefinitely. These were ones from Algebra 2, or probably maybe more of a pre-calc, that you could find what's called an oblique asymptote, which was a diagonal asymptote. Nice thing about AP Calculus, they don't ask for those. They will only ask about horizontal and vertical asymptotes and none of the diagonal ones. So those are our 3 guidelines. Let me take you through some quick examples. What's nice about these is they are very fast. You'll be given a function. You'll be asked to either find the limit towards positive infinity or negative infinity. I think a lot of the ones on Delta Math focus on the positive infinity. And you're really going to focus in on degree and where is it bigger. So for this one, my first one, you'll notice that the degree is the same. They're both x cubed, so they're both third degree. I have 1x cubed on the top. I have 2x cubed on the bottom, which means my limit is a half. If it asks for horizontal asymptote, you'd say, well, there's one at y equals a half. For the next one, same idea, looking at what's happening positive with my positive infinity of my function. This one, both of them are first degree. Now notice, I didn't write it in standard form, and so you want to watch for that. They don't always put the terms in the right order. They do focus on you really looking and seeing. So in this one, you have a negative 1x over a positive 1x, so my limit would be negative 1. Again, that's where the horizontal asymptote would be. That's what the end behavior would be on both sides. And then the third one, my limit as x goes to infinity of this function. This time we have a bigger degree on the bottom. We have x cubed, which means the bottom is growing at a much faster rate, which will create a limit that will get smaller and smaller to 0. Again, creating a horizontal asymptote at y equals 0. I did want to show you the last one because there are ones in Delta Math that get into radicals. I'm going to make a video just about square roots in next, but I want to start with these cube root ones. If it is a cube root, first thing you need to do is make sure, what are the degrees? Are they the same? Are they different? So if you take the cube root of this highest power here, so this is my leading term under the cube root. If you take the cube root of negative 27x to the 12th, you get negative 3x to the 4th. On the bottom, I'm going to just hone in on the leading coefficient. So you actually need to take the cube root first to first see if they even have the same degree. And then once you establish that they do, we can use those limit guidelines. So as I go towards infinity, I would have negative 3 on top, 6 on the bottom. So I would get a limit of negative 1/2. That's going to take you through the basics of it. Next video, we'll start looking at some of the other radical ones that can get a little bit different.